Hey guys, Drew here. Taking a break from playing music tonight because I have the new Shimadzu UV1900 here and I'm playing around with it and thought you guys might be interested in seeing a little bit about what a spectrophotometer is and what it does, and explain to you a little bit about Beer's Law if you don't know what it is, because it's something nobody's really going to teach you unless you go to school for it, and it really is kind of a fundamental concept to understanding the world around you that I think everybody should really know. So I'm going to show you Beer's Law tonight on this UV using a beer. Now, Beer's Law is not named after beer. It's actually named after some guy whose last name was Beer, who lived like way back in Beethoven's time when they first started figuring this kind of stuff out, like the mid-1800s. They started realizing that there was a relationship between the absorbance of light and the concentration of a particular molecule in a solution and so forth, which is what I'm going to show you. I'm going to show you how to actually calculate whether or not I'm diluting my beer with this instrument using Beer's Law. So just to refresh, visible light, infrared, UV, gamma rays, microwaves, radio waves, these are all the same thing. These are all come from what we call photons, which are basically a quantized energy wave that is emitted from an energized source. And all of these have different wavelengths, which they are waves, and they have different wavelengths, and depending on the wavelength will depend on what type of matter can first generate them, and second, what type of matter they will affect. So, for example, visible light is going to affect electrons in orbit around nuclei, whereas something like infrared light is going to affect the vibrations of molecules and things like that. So, visible light is a very small sliver of the electromagnetic spectrum, and what this instrument does is it goes from about the end of the UV all the way up into the beginning of the infrared, from about 190 nanometers to 900 nanometers, and it will scan all the individual wavelengths and produce a spectrum. So the first thing I'm going to do before I talk about Beer's Law is I'm actually going to produce a spectrum of beer and show you guys what that looks like. Okay, so I poured a little bit of Sierra Nevada into this cuvette. You can see it has a little bit of yellow color. Now, the way an instrument like this works is it's basically just going to shine a light through this cuvette out the other side, and it's going to see what was absorbed. And you can look at this and you can see that it's definitely absorbing the light that's coming through, because you're seeing yellow, which means that it's basically going to be absorbing all of the wavelengths on like the blue side, those kind of wavelengths, greens and things like that, to allow you to see this yellow color. And another strange fact is that yellow is the most common color for a chemical for this reason, because most chemicals are going to absorb in the UV range, but some of that spills over into the visible spectrum, and that's where we get these colors from. So what I'm going to do is I'm going to take this thing, I'm going to put this into the instrument, and I'm going to try and measure a spectrum, and then I'm going to show you guys what the spectrum looks like, and then explain Beer's Law and how we do analytical chemistry. Spectrum of the beer, and as you can see, this is showing you absorbance based on wavelength, and you can see as it gets to about 500 nanometers, it starts to absorb a lot until it maxes out. And that is right around where the greens and the blues start coming in, so that's why you're seeing that yellow color, because the yellow up here and the red are not being absorbed. So what I'm going to do is I'm going to take one of these wavelengths, and I'm going to take one where the second derivative is pretty much zero, which means the curve is flat. That way there's not a lot of room for error, probably around like 600 nanometers. And then I'm going to show you guys Beer's Law. So Beer's Law states that the absorbance is going to be equal to A times B times C. A is something we call the molar absorptivity factor. It's a constant. It's going to depend, in this case, on the beer, and I could demonstrate that with a beer. You can easily see that if you look through a bottle of beer like a Corona, it's a lot lighter and a lot different color than a beer like Trois Pistoles, which is going to be a lot darker. It's going to absorb different colors. So these are all going to have slightly different spectrums. And that's something that you have to actually just account for in your measurements. I'm not going to be able to compare a Corona to, you know, a Fin de Monde or an IPA. It's just not going to work. But I can compare the Corona to itself, or I can compare the IPA to itself, which is what I'm going to show you. So that would be your molar absorptivity constant, and that's just dependent on how the molecule is going to absorb the light passing through. And all molecules are going to do this differently. Is for the path length. You can see that looking at a beer that is only a little tiny bit full next to a beer that is almost all the way full, one is going to look a lot darker than the other, simply because you're looking through more beer and more of those photons are being absorbed. So by what we can do in this instrument is we can keep the path length and the molar absorptivity constant by using the same the same beer really in this experiment, and by using one of these cuvettes that I'm going to show you, and then we could just determine the concentration or the absorbance solely on the concentration alone. Concentration. You can see that if I have two glasses of beer that are exactly the same color, and then I actually dilute one with water, one's going to get a lot lighter. And that's because we are lowering the amount of light absorbing molecules per, volume of sample. We're still looking through the same path length here, but one is diluted to about a third of the concentration, maybe a quarter of the concentration, and it will appear a lot lighter because there's a lot less molecules that are absorbing the light that is passing through. So what I did was I made 4 beer standards, and this one is water. This is 100%, this is 50%, this is, the 100% is still in here. And in case you want to see what the sample compartment looks like, on the inside, this is where we put the cuvettes right into there. And these are the 2 light beams that go through your sample and reference side. So I have my 100%, 50%, 25%, whatever half of that is, 12.5%, and then 6.25%, and then 0. It's because I basically diluted each one down 50% in a glass. So I'm not expecting this to be entirely accurate, but you can see how they do get darker as they go on, and that's what we should be able to see and what we should be able to measure. And then we should be able to measure an unknown sample against that calibration curve that I'm going to create with these samples. Okay, so here's my calibration curve. Not so bad for kitchen chemistry. You can see that as the samples go from 100% down to 6.25%, you can see that that the numbers roughly are cut in half, which is pretty much exactly what I would expect to see. They all follow a linear line. So using this calibration curve, I should be able to just dilute a beer and throw it in here, and it should be able to tell me exactly what percent it is. Well, not exactly. This is not the best calibration curve I've ever seen, let's put it that way. But as I said, for kitchen chemistry, not too bad. Okay, so I'm going to dilute down this IPA. I'm just going to measure out 1 shot into here, close as I can. And I'm going to pour it into here. And then I'm going to measure out 1 shot of water. And throw that into here. And I'm shooting for about 50%. So I'm hoping that that's going to come out to be about 50%, and we'll see what happens. I'm not expecting huge accuracy, but anything between 40 and 60 I'm going to say is success. Take this sample that we just made, and I'm going to stick it inside the spec, close the lid, and hit start. Call it unknown. and hit start and see what we get. And we are getting a concentration of 54%, which is pretty good for kitchen chemistry. Absorbance of 0.032, so you can see that's right around the absorbance of the 50% standard of 0.028. And that is how we would go about calculating something like this. Keep in mind, normally you're looking for a specific molecule, not a substance. Beer is a composite substance, a mixture, a solution. It has ethanol and water and probably hundreds of other chemicals in it that are light absorbing chemicals. So normally if you're doing this for real, you would be doing this looking for a specific molecule that's absorbing at a specific wavelength. But it just goes to show you how robust this kind of technique is, and how Beer's law is really kind of ubiquitous throughout analytical chemistry. Because this is what we do. We produce these calibration curves and we measure these samples and tell you how much of what is in what. Now, without chromatography and without a mass spec, I can't tell you what is in here, really. I could maybe guess, but I can tell you how much of it is in there compared to a known standard, and that's exactly what we would do with an instrument like this.